Esse é o online, o pessoal vem assistir.
Normalmente é só as sessões virtuais, é quando as pessoas. Bem, temos que colocar sempre o online, porque pode desestabilizar alguém.
Claro, sim.
Mas está impecável. Já está com o som
Sim,
e a câmera.
falta só. Para depois colocar o tempo do coffee break.
Leva uma hora para
Se está bem, costumo, quando eu venho, tenho vindo para esta sala, tenho que experimentar sempre, mas também eu era da parte da tarde, hoje eu me digo sobre isso.
Eu vejo a minha também ser com aqui está o professor em
Ok, é isso. Assim depois.
Isto aqui é o final do
Confirmar. Dormi longe, cara, dei a volta de novo.
Sério?
Ninguém não conheceu. Aí eu dormi, quando eu voltei, o pessoal faz assim.
Só testar sempre que é PowerPoint. Tenho que testar aqui.
Os dias deles. Emoções. Mas eu vi bom, hein? Nossa, perfeito, renovado. Sei que esqueceu também, tem uma história. Essa foi boa para ver. Eu juro que eu não acreditava.
A gente demorou uns 40 minutos. Não, mais.
Eu olhar para nós.
A gente chegou.
E voltar.
A gente chegou, o jogo estava começando. Aí deu uns 40 minutos. Não chegou, vamos para lá, sabe se o ônibus chegou. Se o ônibus chegou, aí o ônibus só chegou.
Deu que você passa de novo para uma garagem, né? Hoje você já deve acordar pelo menos que eu tô.
Aí eu vou funcionar da Colônia, você vai ficar aqui na universidade, fica com você, né? Vai cuidar.
Nossa, estamos aqui já na universidade.
Eu vou ver, tinha ligação.
Quem chegou?
E essa loja? Eu já está feito. Só falou.
A luz, graças a Deus, aconteceu. Não sei se nunca tinha tem alguma visão de intervalo.
Eu falei, não, porque eu então
Era uma solução que eu ia falar. Deixa eu ver aqui, que isso é nós vamos preparar essas coisas.
Voltando ao aviário. O passeio aviário, logo, o passeio. Por causa do calor. É só por isso, nada mais. É muito giro a cidade, mas o calor. Mas lá também é mais fresquinho, tem mar. A partida será mais baixa um bocadinho. Mas vocês lembram que também é calor, não é? Este verão é assim.
é muito calor também, não?
Pois.
Lá na minha região tá muito frio agora.
É que agora é muito frio lá.
Depois lá é inverno, não é?
Se você estiver lá, bem, comparado com aqui,
Não, mas Paraná não se legal.
é que o Paraná faz muito frio.
Precisávamos dessas temperaturas.
Mas não tanto, né? 40 graus.
Hoje está bom para uma praia de Rio, uma praia.
É. Eu vim ouvir na rádio 41, mas mas
É que aqui, eu acho que no Brasil o pessoal é um pouco mais preparado, mais acostumado, né? Lá quase
Mas é assim, se for preciso aqui está uns dias a menos, ou assim um tempo melhor, de repente sobe muito, no outro dia se já aconteceu de estar hoje nos 30 graus, por exemplo, e amanhã nos 18, aos 15, portanto, nós não vai crescendo ou diminuindo a temperatura, vai dar um salto.
o Brasil dá um salto, fica 9 meses.
Eu pessoalmente gosto mais do inverno, agora é o fim. É que esta zona de Braga então é muito
É
quente.
muito quente, né? Mas acho que, em geral, vocês gostam de prova. Eu gosto.
Eu não.
Você não.
Eu devo ser uma portuguesa.
Eu vejo esse pessoal
Esse-
viaja muito.
Sim, eu, por exemplo, prefiro viajar mais inverno. Eu não gosto de pacientes com muito calor, já chego ao nosso. Mas é depende das pessoas, sim, eu gosto do calor.
acho que-
Inícios, não é?
Isso.
Tem a. Ok, só faltou.
Nós não ligamos.
Eu acho que talvez aqui o programa subiu mais da Oriente, né?
No litoral.
Alemanha, esses países. O pessoal acha bastante assim.
Pois.
A Suécia.
Aqui, bem. Este lado.
Seria uma semana naqueles. Ali na questão da barco lá. Eu tenho outras casas, eu tinha lá mesmo sempre coisa.
Tá bem, eu deixo. Só deixo.
Surreal. Assim, todos os parques, semana toda, então, os primeiros, primavera. Quando eu cheguei lá, e assim, é uma semana, assim, e eu não vou subir lá.
Agora o seu pendrive não é reconhecido.
Cuidado, à vontade.
Foi do outro lado, do outro lado.
Depois, já deixei dos dois.
Tem outra porta, assim, ele toca verdade. Aí, agora,
Quando saiu. Ah, já está.
Não, esse não.
Ah, já está.
a próxima da primeira.
Vai tentar
Vou passar isso aqui.
Tem outra usar que você vai.
Eu mostro a você. Agora não quero. Tenho.
Aqui eu não sei o que é. Eu não sei quantos meses de inverno e não sei quantos de inverno.
Sim. Mas não sei bem o ditado, mas eu já o ouvi, sim.
É.
Deve ser para aí 3 meses de inferno.
É.
Julho e agosto.
9 meses de inverno, 3 meses de inferno. Deve ser algo assim.
Deve ser assim. Eu já ouvi já, mas não sei quantos meses.
Praga, são os extremos, né?
Ué.
Isso apareceu um medo.
Pensei que não.
É, esse aqui.
Bonito.
Uhum. Já fala aí, eu fui achar que era jeito, mas eu vou chegar
Aí
aí.
é no rachão, no andar de baixo.
Deixa eu ir lá na sala.
Ok.
Não só ouvir, não, eu estava só estudar, eu inglês mesmo, vergonha. Mesmo.
Memorado.
É Sandro, não é? Sandro. Tem alguém a ver? Good morning. We can start this session. The chair is not here yet. In this session, we have 5 presentations, and the first is presented by Natalia Frederico, and the title is Surgical Instrument Tracking, a lightweight YOLO approach across diverse domains.
Sure.
That's okay.
Okay. Você fez pergunta. Já pode começar? Hello everyone, my name is Natalia and I'm a PhD student at the Federal University of Pará and I research at our technological innovation laboratory, and my research area is machine learning applied on health sector, but today my presentation is about I will present a lightweight methodology for surgical instruments detection across diverse environments or domains. The presentation is organized into 6 steps, to 6 topics. Starting with the motivation, purpose, going to the background to challenge, the experimental design, results and discussion, and for concluding, the future work. To begin, before we dive into the technical details, I want to start with a common question in this field and the core concept of this study. Artificial intelligence is not a replacement, but it's a tool, just like a grasper or a hook in a surgery context. And robotic surgery is not a new routine in some countries, but AI is slowly changing this perspective with the new way of interpreting modern surgeries. In medical training, the ethical priority is never the first time on a patient. Simulators are essential, and AI can provide automated feedback on a student's performance. However, widespread implementation faces significant challenges such as complex visual interference and high computational costs. Therefore, the purpose of the study is to evaluate a lightweight YOLO architecture to specifically address these two challenges. Looking closer at the background of the study, the transition to real clinical scenes faces significant visual challenges. As the image illustrates, the surgical environments are highly dynamic. Algorithms must deal with blurring, bleeding, crowded surgical instruments, reflection on the instrument, broken view, smoke, occlusion, lens fouling, and blood stains. And in a computer vision models, which can easily confuse these standards, these difficulties on our visual channels. To handle these issues, the literature explores several paths. One-stage detectors, like the "you only look once," as it stands for YOLO, that is the main purpose of the study. YOLO family are widely used because they offer the speed necessary for real-time tracking. On the other hand, pixel-level segmentation networks provide exact boundaries, but they demand higher processing power and are typically too heavy for continuous vision. And the emerging trend today is the foundation models, technologies like the segment anything model that offers power recognition but require massive computation. This brings us to specific research gaps. Many existing models have a high computational dependency. We struggle with generalization across different domains and lack pedagogical feedback metrics. Because of these gaps, this study proposes a paradigm shift, moving away from maximum precision at any cost to focus on resilience, efficiency, or modest hardware. To ensure our reproducible methods, the methodology follows the cross-industry standard process for data mining, or CRISP-DM cycle. There is a data-centric framework, and the major challenge of this study is all the phases of the data. During the preparation data, there was a lot of heterogeneity. There were different formats of annotations of the images of the videos. So to build a robust system, 3 distinct data sets were integrated, each one with their own kind of annotation. So this required converting different types of annotation, sequential boundabox, skeletal key points, and pixel mice into a single universal taxonomy for the YOLO architecture. During the training process, this technique, mosaic augmentation, was applied. In the grid, this technique merged 4 separate surgical images into one single frame. It teaches the model to identify overlapping tools, varying scales, and different backgrounds simultaneously, improving generalization without the need for the massive computational power. Moving to the quantitative results, the model achieved a mean average precision of 90% in general, and a global F1 score of 0.87. As demonstrated by the precision recall curve, the system provides accurate instrument localization while maintaining computational efficiency. Important thing to notice, the model addresses the natural classing mass imbalance found in surgical datasets. While Grasper is the most used instrument tool, there are instruments that are rare, like the specimen bag, or compiler, irrigator, and even they could maintain an excellent accuracy, reaching over 99% of precision. And qualitatively, as in the sample frames, the model successfully tracked multiple interacting tools across different domains, ignoring visual noise like smoking and occlusion. To further test this, a zero-shot test was conducted using unannotated surgical videos directly from YouTube, and the model maintaining consistency, tracking under new conditions, proving that unifying the datasets effectively helps the system to adapt to unseen environments. To conclude this study, the first main contribution was to unified framework. We unified 3 different data sets and annotations into a single one, a YOLO annotation form architecture, and we also identify specific limitations. As we use cloud storage, we faced some bottlenecks, like input-output bottlenecks in cloud systems that requires localized storage. And we also discover vital blind spots. The model occasionally misclassified closed Caesar as immigrators or completely dark backgrounds, proving the need for background-aware learning to provide anatomical context. And ultimately, the model achieves a functional balance between efficiency and accuracy. And next steps, future works, include target data augmentation and deployment in educational simulators with pedagogical metrics. And for to finish, our study is an open access study, so you can scan the GitHub link. It is publicly available. And to finish the questions you may have, and thank you for your attention.
Questions? No questions? Yes.
Yes, it's very good presentations, and this research is very interesting because I'm working in the domain with machine health, and
Yes.
working with human health. It's very
Yes.
complex organs. I want to ask you, as long as you know, normally researchers are only using the like animal to in their research, and you're using humans. In this type of set, are you only focused on one specific position, like organ or something, or whole body?
Oh, we take 3 different data sets, and one is for colorectal surgery. The other is the from the teeth surgery, and the other is laparoscopic surgery. So it was 3 different domains, 3 different environments.
I don't know.
But it was different parts of the
position
farm.
of the body?
Yes, it's different parts of the farm. It's the teeth, the colon.
Okay.
Yes.
It's very interesting.
So I have a quick question. On your slide 16, you showed the results, but they're only for single instruments, right? Not for a crossed instrument or overlapping.
Yes.
Yeah, so it's the actual for classes, right? In the 3 setups.
Yes. After we unified the 3 data sets, we took the metrics for individual for each instrument. Is that the question?
Yeah, that was the question, but that you don't have any kind of precision recall results for mixed instruments,
No.
including
I didn't.
the sections.
For each challenge, right?
Yes.
No, not yet.
Okay.
But it's a good idea.
Okay.
To that. Questions?
Okay, that's
Takie pozycje, że są você volta então as coisas mas é que a coisa vinha agora, né? Que eu precisa de algum e apresentar no celular. Quer lá não?
Okay, the second presenter is Lucas Rivas with work whose title is From Random to Pre-Trainings, VIT, Backbones for Improved Feature Extraction, Application to Diagnosis with Sensor Images.
Thank you.
Yes.
Hello, everyone. Good morning. So, I'm Lucas Rivas. I'm professor at São Paulo State University in Brazil, in São Paulo State, in São José do Rio Preto. Luan and Ana Beatriz are master students, while Kazaka is a colleague of the department. So our works from random to pre-trained VIT backbones for improving feature selection application to diagnosis with sensor images. So this is the summary of this presentation. VIT, Vision Transformers, is the state-of-art main tasks in computer vision, and its adaptation of transformer to the language models, and basically use attention to capture global partners in image with strong results in many tasks and applications. In general, the VITs are pre-trained in large data sets, like the ImageNet, and then adapt to other specific tasks. So, the challenge is how to capture microtextual partners using VIT, because the VITs has a pre-trained bias, because it's pre-trained in the ImageNet, and the ImageNet is a large nature data sets. So the focus on the ImageNet is object recognition and scene recognition. So in many applications, like in medical image, we need to analyze the micro partners, fine partners in the image to separate the different classes. So the texture is spread across the whole image and not in one object. So few works use VITs as a backbone to extract microtextual features. In our group, we have some works in this direction, but this is the first work using biosensor images. So I will explain the next slides, but biosensor image is not a biological image; it's a mature microscope image. And in this kind of image, the microtexture partners is the main group. Okay, we propose in this work to understand how the architectural components in VIT backbones capture text information from the sensor image, the biosensor image, and we studied three token-based feature extraction approaches: the CLS, the gap, and the combination of CLS plus gap. We propose use the random VIT to reduce the ImageNet bias and test if the architecture by itself can extract good texture features, and the fusion of the random and pre-trained features, but combine both kind of information. And finally, we test in our experiment 10 different VIT backbones or architectures. So architectures backbones similar. Yeah. Okay, this is the application. So the medical diagnosis with the biosensor microscope image. So a biosensor basically is an analytical device that detects a specific analyte, like PCA3, for prostate cancer diagnosis or for COVID. So here we have different images from the mature biosensor. So they are microscope images. And the traditional techniques in physics and engineer is use electrochemical or optical detection in these biosensors. This is one the first works using the image of the surface of the biosensor. So the diagnosis signal is in the microtexture of the sensor surface. So this is a hard text problem. Hard texture problem. Okay, introducing the transform. What it was introduced in 2021. So this is the traditional image of the architecture. So we have the image, input image. This input image is divided into fixed size pads. So here we have the pads of this image. Then these pads are converted into embedding vectors using a linear projection with a position encoding to localize the pad in the image. And these pads are processed using a sequence of transformer blocks. The transformer blocks are the layers of the architecture. T in general is 12 in this architecture. Each block produces a matrix of token beds, the X matrix. I will explain the next slide. And this matrix has any, and that's the number of tokens, and these the hidden dimension. So basically, is the hyperparameter of the architecture. So the token matrix X includes two informations. The CLS token is the first row of this matrix, and CLS is classification token. So provide a compact representation of the image, and the model, the head of the model, the MNP, the last layer of the model, use this token, this embedding to classify the image. And the other rows are the special tokens. So these special tokens are associated with the image paths and code more region information. So both types of tokens contain complementary information of the image. And pre-train and random VHs. Pre-train VHs, typically the VHs are trained on large scale data sets like ImageNet with millions of images, but may introduce bias related to natural image statistics of this data set. And the random VHs are the model with random weights. We did train these VHs, so the weights values are random, so no pre-training. So we don't have a bias of the data set in this case, and recently we have in the literature some works using random transformers architecture to search the best architecture to a problem. So this is the overview of the methodology. So the biosensor image, the pads, the embeddings. Here's the VHT backbones and the transform blocks. So we get the last token matrix of the last transform block, and we get the CLS row, and here we apply the global average pooling in the columns of these rows. This is the spatial tokens. We have two representations, CLS gap and CLS plus gap. So the backbone is used in this case without the classification head. So we use the backbone as a feature extractor, as a classifier. And the representations are obtained using the output matrix, the last token matrix, the last transform block. So we have two kind of VAT models, the pre-training on the ImageNet and the random VAT. And we test the three tokens kind of representations, the CLS representation, the spatial token, so basically it's the global average pooling over the spatial tokens, and the concatenation of both representations. And we also propose combine the random and pre-training representations. So the random presentations use the same approach, but the model is random, the VAT is random. So it's the same overview, but using this backbone, the weights. So the experiment setup, we test two data sets, different data sets, the PCA3 data sets and the SARS-CoV-2 data sets. We use 10 different VAT architectures, and we compare with fine-tuning in CNN baselines. In this case, we use the same VAT backbones, but using a fine-tuning. So the two data sets, the PCA3 and the SARS-CoV. This is the SARS-CoV, and this is the PCA3. And here is the selected VAT backbones. So 10 different VAT backbones, the pre-training of these backbones, and the cost and the size of the representation. So the first, the data sets will have two different tasks for the same image. The binary task, so basically it's positive or negative. So the biosensor was exposed to the light or not, and a multiplex problem. So here is the binary classification of the two data sets. So the results using pre-trained for the three different representations, CLS gap and CLS plus gap, and the random plus pre-trained representations, VAT backbones. And the last column is the fine-tuning, and the same VAT backbones. So summarize these results, the combination, the best results was obtained gap or CLS plus gap. So it's the higher mean accuracy. And the best results was obtained random plus pre-trained features. So combining these two kinds of features. Here's the multi-class classification, SARS-CoV-2 and PCA3. It's more hard task because you have more classes, and the difference between the images is small, the micro textual partners. So the best results here is using the combination of the CLS and gap and random plus pre-trained features. And here's architectural analysis. So it's the comparison of feature selection by random and pre-trained. So in this plots, points on or right of the diagonal, the line, the random backbone is better than the pre-trained. So this figure show the importance of the transform architecture itself. So just not using training. this is a attention maps analysis. So why do random VAT is obtaining interesting results? Random VATs, this is the attention. So what is the place the model is looking at the image? In VAT, the attention is more spatial distribution in uniform way across the image. And the pre-trained VAT, the attention is focused on specific regions because of the bias of the object recognition of the image. Okay, this is a comparison to a CNN baseline models. So this is CNN baselines, convolutional networks. This VAT backbones, the results, the better results was obtained. The best result was obtained using the VATs when we compare to CNNs. So improve the results. So to conclude these presentations, the VAT can serve as a powerful feature extraction for biosensor image without any fine tuning. So this is interesting because this presentation can be used to classify or to retrieve for many tasks. It is an image presentation, and in this work we test to classify the images using a simple SVM classifier. So we test the 3 token based representations, and the best result was obtained by spatial tokens and the combination of these 3 representations. And combining the random and pre-trained features improves the performance in the 2 data sets. The proposed approach outperforms the fine-tuning VATs and the baseline CNNs. And as feature work and limitation, we need test multi-layer feature aggregation. So we use the features from the different layers, the different sequence, different transform blocks. These are we are working this how in our laboratory and show this performance using benchmarks and other applications, medical applications, or other kind of applications. So, well, thank you very much.
Questions?
Okay.
Lucas, can you go back to slide number 10? I think you listed experiments. Yeah. Oh, sorry, that wasn't on 11, maybe.
Yeah, 11.
Oh, that was 11, sorry.
Okay.
It was very good. Okay, that was my question. That's the backbones. They are already done by the library.
Yeah. It's the team PyTorch library, and we get the pre-trained backbones of this library.
Okay.
We didn't train the backbone.
You try, just out of curiosity, if you try or consider another supervised classifier, because SPMs are often beat by remote forest.
Yeah. We use this classifier because in general in the literature of the image, the other works using the simple classifier like SVM, but this is an interest point for future works using another classifier like random forest or other.
And finally, last comment, on slide 17, you mentioned that you explained to us that the pre-trained fits for the random fits are better because they don't have the bias of the purpose of the pre-trained ones, right?
Yeah, it's a hypothesis of this work because when you use the pre-trained models, we have a strong bias of the object recognition. So use just the pre-training, the results are not good. For example, here, this is just the pre-training with fine-tuning. So the results is in general are not good using just the pre-trained backbone and the fine-tuning. So our hypothesis is the attention is more distributed in the image. That's important for this problem because texture is across the whole image, and you need obtain the fine partners in the image. So random backbones, the model looked at the whole image, the pre-trained whole in specific regions, and
That's I think it's very interesting because most of the people when they start with this kind of using image lab data, they don't do this. They just use the raw data.
Yeah.
Go from there.
Yeah.
So it's a very interesting result, and I suggest you explore that even for the other models. For example, people are developing a lot of tools on plant recognition and disease recognition. They are more like textures and block based than beef based. For example, if you try to identify diseases in coffee leaves or in cacao, it's more a texture problem than a blotch problem, than an object. I don't care if it's what's the object. I care about it.
The texture information.
So, thank you very much. Congratulations on the results.
Yeah. My master's students are working in this direction, and we work with also with leaf images from to classify the different species or diseases in leaf images. But this is a first result of the master's student, but we are working in this direction to do this to improve.
Okay. Thank you very much.
Okay, thank you again. Okay, the third presenter is Vinicius Mota, and with work whose title is Analyzing Optimization Trade-off between Energy and Model Convergence in Federated Learning. Okay.
Thank you. Good morning, everyone, for being here after that. Here. And I'm present the work of master student Nilo Lousada that's advised by Professor Maria Claudia Boeres. And this is a collaboration between the optimization lab of GUPS and the network lab from OOPS. I'm more a network guy, so the questions about the optimization itself can be done directly to the output that is from the optimization field. So let's see this. So just to clarify, what's federated learning? Now it's a common in computer networks, but just to clarify here, in federated learning, instead of centralized learning as present before, every machine learning running in a single cell, to have that local cells train its model and then just share the weight with a central server. Why this? This is just because the greatest motivation is about privacy, where you keep the local data secret, share on the weights, and the weights are averaged you took the average of each client in the network and average these models to create a global model. It's clear that federated learning, because of this, the accuracy of score is usually lower than the centralized version, but you have, as a trade-off, you have a strong privacy issues of the data that is not be shared. This is quite useful today for health. Hospital can train its local models and then just share the models and not share the data itself. So it's being used. But just a quick history. This idea of federated learning born with cell phone and Google Maps keyboard. Google Maps want to learn which department people are typing with just crossing the fingers, but don't want to share the data that people are typing. So they train the model locally and send to a central server, but there's a problem when you go to IoT or cell phones or mobile, because you have battery issues and you have processing heterogeneity issues. For instance, some cell phones are Snapdragon processor. Someone is processors that so you don't have the same idea of what I did. The same idea of processing. So the problem state here is that given a federated learner network, jointly choose the CPU frequencies of the device and the how to train. By how to training mean each time I receive a global weighted model, average model, I want to train again with my local data, my new local data, and send again the updated weights to the server. But it's called a hard training, but I want to minimize the energy while preserving the accuracy, which means I want to create a model that will increase the accuracy in the final model. Just to clarify, because sometimes you can change the model, but when your model is average with the global one, the accuracy can decrease. This is a problem in federated learning because there are several clients, the heterogeneity of data, so it's a hard problem. The gap here we're trying to tackle is just about the CPU frequency as a decision variable to decide which client will participate of the client without degradate the accuracy and without degradate the energy of the device. So there's a lot of federated learning began in 2014, 12 years ago, and these ideas of optimization is not new. I will highlight that we apply the Karush-Tucker KTT, known as a KTT, as a convex optimization directly into a realistic container-based scenario called MiniNet. That is a tool developed by our group. So we are applying our optimization algorithm to try to balance this idea of CPU and energy. So the system model. Consider that you have aggregation server, and these aggregation servers, you have a lot of clients device, and this client's device, each client has its own CPU frequency and capacitance coefficients, which means how the device deals with energy consumption. So each client, the aggregation server must decide which clients will participate of a training of the network here. And to this, each client will report its current data size. Just this, did not share the data, just the amount of data they have to train the local model. The aggregation server then select the participating clients, and the aggregation server then solve the optimization model, which assign each client a frequency that they must work. The main idea is A client that can increase accuracy with low frequency, let's increase the frequency of the device, so you can save the energy of the device instead of put everyone to work in the most frequency as they can. And handling the aggregation server applies federated average. It's a classical algorithm, basically to take the weights and take the average of the weights of each client. Basically, that you assume that every weight has the same size of the vector, so you can just apply the average of each position of the vector. Without going in the math itself, but we have two variables that we want to optimize here: the computation training time and the energy consumed by the training, the local model training. So the energy is basically based on CPU cycles required to train, and the energy is basically based on the capacitance of the chipset. That's a parameter that each chipset has its own, multiplied by data and CPU frequency. And again, with that. So this is a bio-objective optimization problem where I have to try the trade-off between computation time and consumption, trying to minimize this idea. But here's an important factor that we try a kappa parameter. It's a hyperparameter where I try to do this with the time of the CPU plus the sum of energy consumption. That's the optimization model that we try to solve. Frequency here is the lever, because the time required to complete a training round is inversely proportional to the CPU frequency. How low the frequency, higher the computation time, but lowering CPU frequency quadratically reduce the energy consumption. So you have a gain when you reduce the CPU frequency. So how first we just try to manage this kappa value, and you achieve that, okay, if you achieve log 0.75, you achieve an equilibrium between maximum energy savings and minimum latency here. This was pre-processed before with several values of kappa to understand which one would provide the better results of this constant in our model. And the Lagrangian and KGT solution. This algorithm is not ours. We based this algorithm in the recent literature, which means I divide the clients in 3 clients. One is the bottleneck. Clients slow, so slow they drag down the whole network because they are too much slow. The fastest clients, clients are high efficient clients that finish early at low speeds. And the optimizer, the remaining scale device. So you have the device that's slow, that this is a problem device because they can train locally fast. And the optimizer is the one that you decide the frequency for them. And this algorithm, the good news of this algorithm is that it's linear. It's a linear algorithm, so can run in log n each round. To the experimental setup, you used a MiniNetFed. It's a tool developed at our lab. MiniNetFed was present last year at CCON. And to this, it's a container-based, so you can, different from a simulator and MiniNetFed, you can, each client is a container, a Docker container, so you can set the CPU, you can set the memory, you can set the heterogeneity of clients as a normal client. And you make a lot of ablation tests with several hyperparameters to understand where this algorithm would solve the problem. And the energy, for the energy consumption, you use the classical one, which is the frequency of this, the frequency multiplied by the data. and use it to just the MNIST for this work, just the MNIST, that's a classical data set with true distribution, mid-IID, mid-independent distributed data, all 10 labels per client, unbalanced quantities, and non-IID. Each client sees only 4 random labels, therefore, no client has knowledge about all labels in the data set. EK equal 10, therefore, which no device sits as its frequency bounds. So compare the strategies here. We provided 5 strategies. Standard, all clients, list energy client selection, only device below the previous round average consumption. Let's see. I want to save energy, optimize it, frequency set by our algorithm, optimize and fix the frequency, frequencies, but the round stops at the optimal time. The optimal and least energy is the least energy, but with the optimization model applied itself. So what we observed here is standard is the least efficient, or just run the federated learning as expected, of course, is the least efficient in energy consumption. And when you optimize and put a time of computation hardware, we observe that you have the most energy saving. And the same here appears on non-IID data, where the optimizing and fixing that you want to consume least energy, you obtain the okay, but how this affect the accuracy? The accuracy is not affected at all. The standard here, it's our upper bound, it's the normal model. Of course, if I put too much optimization, you decrease the consumption, but you also at the end we almost achieve the same result as initial one, but with a cost of increase the number of rounds to achieve convergence. But the good news is with non-IID, where the data is not equally distributed among clients, the result is totally different because the standard, okay, it just achieved the convergence faster because its standard is running the high frequency of data of the CPU, but the other strategies that we implemented just achieved the similar accuracy, consuming too much less energy. So the payoff here, the payoff putting this in just one graph, the energy consumption for mean accuracy shows that, okay, you can achieve accuracy higher, but with a higher cost of energy, where you can achieve the same accuracy with almost the half of energy. Going to conclusions. Strict round time control saves a lot of energy, but with a little decrease of the accuracy of the model. There's a trade-off. You need to choose whether you want to save energy or you want to optimize the model. Frequency optimization showed good results. It saved up to 30% of total energy in our model. Theory to practice. The analytical optimal holds up inside a realistic container-based emulation. That's it. We're not just simulating, we're emulating our results. As future work, you aim to add the number of local epoch as a decision, because you saw that if you train more epochs, sometimes you just achieve the high accuracy, but you also consume more energy. So you want to optimize this. Integrate client selection directly into the frequency model. And you must, there's a limitation here, I didn't say, but must say, the energy model fits well for CPUs, but GPUs, GPUs, NPUs, TPUs, there are totally different energy model that you must consider, because today we run in GPU, NPU, TPU at the edge itself. You must scale the evaluation for more hosts. So thank you. These are the autos for those interested in federated learning emulation. This is our tool, MiniNetFed. It's an open source tool. So thank you.
Thank you. Questions?
Okay.
Can you explain a little bit more about bottlenecks that you showed in slide?
This one.
Yeah, so is there a scenario where the bottlenecks should be just because they are freezing the operation, or you can move data?
Yeah, the strategy, if you look the strategy of earning, just the standard, every client will participate. But in the strategy of just efficiency, the bottlenecks will be removed of the emulation. That's why, good question, because that's why the accuracy is lower, because you removed some nodes from the training rounds at some point. But if you want to wait for the bottlenecks, it will be the standard behavior where everyone participates. But in the strategy, I think least energy, this one will remove the bottlenecks by itself.
So I can write. Instead of waiting for the bottlenecks, I can just ignore them.
Exactly. The Lagrange relaxation and the KGT, what they do is exactly that. Select which client is taking too much time or taking too much energy and remove them from. That's the difference between it's basically each strategy here, you select the best client based on the strategy that I want. If I want to just save energy, I remove that one that took longer time because you consume more energy. If I want to optimize, I will set the frequency of that one that faster, that it are consuming energy, but are too fast. So you can just drop off the CPU frequency of them. And the last one, I will set the frequency of the faster, but also remove the slower ones from the computation. So
The data is centralized.
Sorry?
Is the training data centralized?
no, each client train its
Data. So we lost accuracy, but
yeah. Okay, that's a problem here. For instance, if one client just one client has one label, and another of the clients has the label. So if this client is removed from the training round, you have the problem because you didn't train that label in the model. That's a problem here because this is a strict problem of federated learning. You don't have no idea about the data. You just have idea about the model. If you never saw a label, you can do nothing. But it's a
the metadata, so I can say, okay, I need to wait for this guy even if it takes too long. We don't have this information.
no, you're blind. The aggregation server is blinded by the data. In this case, in this solution, just the size of the data is the only information they have. The aggregation server has about the data itself.
Thank you very much.
Thank you, René.
Talk later.
No more time,
Yeah.
no more questions, sorry.
Okay, thank you.
Está para precisar isso.
Pode ver.
So the report presented is Luis Rodrigues. With the work whose title is Topology Aware, distributed assembly learning using the VCube hierarchical hypercube overlay. Okay.
Thank you very much for the presentation. Good morning, everyone. So it's a kind of similar solution presented by Vinicius before, but in this case, we are using a distributed ensemble learning instead of a federated learning. So the main difference is that we don't have a central organizing, just thinking about a totally distributed organizing system. It's a joint work with my colleague, André Brum, and his student, Charles Salles, that finished his master last year. We are from the State University of Paraná in Brazil. So the main motivation is that IoT and edge environments generate massive distributed data sets, but centralization of this data introducing a communication overhead. So in this case, we are also thinking about privacy restrictions, helping prevent data sharing. And in our solution, we are more focused on distributed systems that must tolerate node failures. So if a node is corrupted or is crashed, so how can we deal with this and reorganize the topology to get all the information that we can from the network? So in this case, distributed learning can enable models to be trained using decentralized data sources, such as federated learning, but without constraints about a centralized processing. So the challenge is, how can we build scalable and fault-tolerant distributed learning systems using, in this case, the VCube topology? So just for a comparison, if you use, for example, similar solutions in the literature, use, for example, tree-based dissemination, okay? But in tree-based dissemination, we have always a root or nodes that are up to the root, up to the tree. So if the root fails, for example, all the tree is broken. If a higher node breaks, all the below nodes are lost in the network. If you use a centralized node, we have a fault, a high bottleneck risk, because if the main node fails, all the nodes are disconnected. So if you use a hypercube-like overlay, I will show you how we deal with failures. We have a low impact about the failures of any nodes, because the hypercube can reconfigure to remove these nodes from the topology. And you have a high fault tolerance. Okay, and of course, communication cost is a main goal of this work as well. In hypercube, we have logarithmic properties that I will show just now. So the goal is create a solution. We're not proposing a new model or a new federated learning or a new ensemble learning model. We're just organizing the system to improve decentralization, fault tolerance, low communication overhead, and high prediction accuracy. Okay? So the VCube is a virtual topology that was proposed a couple of years ago. I have been working for more than 10 years with VCube, and it's a hypercube-like structure because it's similar to a hypercube, but it can change the edges as soon as a process is faulty. So consider that it is a VCube with 3 dimensions, and we have each node connected to log-n nodes. So in this case, node 0 is connected mainly to node 1, 2, and 4, and so on. We can use the IDs to do that. But if node 4 is faulty, is crashing, or not responding, we can find another node in the hypercube organization that replaces this node and keeps the logarithmic properties. So, for example, from node 0 to node 7, we have at least 3. In this case, in a 3-dimensional hypercube, we have 3 steps. So each path here can be chosen. It will be at most log-n nodes. So even if 4 is faulty, to get node 7, I can use this shortcut to get node 5 and then node 7. So for any kind of faulty configuration, we always have a different path that we use it to reconfigure the nodes. So consider that the network is fully connected. but we are organizing the nodes virtually in the network. Okay. Well, VCube has many applications, especially for failure detection. Let's start with that. I use VCube for many solutions in broadcast, using this dynamicity to create trees, to propagate message in this topology, to mutual exclusion, pub subscribe systems, CRDTs, and so on. Well, in this work, we propose an architecture where we have local data sets. So each node keeps its own local data set, never share data with other nodes. We have a local training. So first, every node trains, it's classified independently. We can also use different classifiers because they're not. We do not have to aggregate these models. Then we only the training models are disseminated to all the nodes using VCube communication protocol, and then we can ensemble this classifier using our receiver models and have a fully model that gets information for all nodes that are correct. If some node is faulty, as Vinicius presented before, of course some data can be lost, but as soon as the node recovers, the data can be used again. So how data never leaves the original nodes, so it's about privacy, etc., which can preserve the privacy and significantly reduce communication costs because you need to exchange just the model and never the data. In the dissemination strategy, first, all the nodes knows only its own model. So node 0, in this example, with 8 nodes, for example, we have node 0, 1, 2, 7 training locally, and then they exchange data using the hypercube hierarchical topology. So first we try to exchange models with my first neighbor, and then we can, for example, node 0 exchange models with node 1. In the second step, node 0 can exchange models with node 2, but it also have the model for node 1. So node 0 will send models from 1 and 0 to 2. And the last step, we receive all the information because all these models are combined to have a final model in the topology. So every time a change occurs in the network, we can reproduce this procedure and exchange the models with the neighbors in the hypercube topology. So just for like test, to use some different types of strategies. So some strategies to evaluate, so majority voting, some product rule that are really common to compare the aggregation, the ensemble of these models. You use also a data set, a motion sense data set with some activities classes. So downstairs, upstairs is a well-known data set in the literature. And we also use a multi perceptor because it's suitable for this kind of problem, multicast problems. We also use a 730 training testing strategy. And we comparing 3 different scenarios, a balanced one, an uneven size, and a non-IIZ scenario to see how the model reproduces how the model improves the accuracy in the VCube topology. So I just had some parts of the results, of the full results are in the paper. But here we can see the time to training the models centralized and distributed. So of course we are reducing the number of classes in each node. So of course we have a parallel execution, and we get a lot of improvement related to the training time. In this case, we also are losing accuracy, of course. I have to improve, I have to augment the number of classes to have a better accuracy, but we reduce the time to train the models distributed. Here we can see how the accuracy is increasing when we exchange the round, when we execute the rounds of PQ. So for example, when we send two models, we have a low than 56% accuracy. When we have 4 models, when we execute the first round, we get the models for all neighbors in the second level. You have an improvement, and we have 8 nodes that have a higher improvement here. And so you can continue ensemble these models to have a higher accuracy in the system. So model sharing progressively improves prediction quality because you are receiving more data from more models for different nodes. Here we compare the VCube solution with a decentralized tree that's common in this kind of solution. So in all scenarios, we can see that the VCube improves accuracy against the tree topology because we have faster and how can I say, a more fault tolerant topology to get all the data from all the models from the system. And here we execute some tests, including some faults in the system. So we just crash some process in the system to see how the final models will be compared. So you can see that despite of failures, performance remains stable. So we can continue to get information about the network, even if a fault node is present in the system. So one or more fault nodes present in the system. So increase dependability, availability, and so on. And just for finish, how we can see, here we can see the communication cost. So consider if you have to receive all the data from all nodes and from the network, we have 306% more data being shared in the network. If we are considered just the model, we have just a small piece of information being transmitted to each node in the system. Okay. And consider that's not a centralized solution. So we have like a broadcast in the system, but the broadcast using hierarchical steps to exchange information during the. So the main results, so we can see that we have an 87% reduction in training time. We have up to 19 higher accuracy than using a tree dissemination strategy. That's a normal strategy. We are more robust under node failures, and we have a lot of improvement in communication. And to do all this, we have on-login communication rounds that is related to the topology that you improve implements. So in the end, we learned that communication topology plays a crucial role in distributed learning systems. The proposed VCube-based architecture provides scalability, fault tolerance, reduce communication overhead, improve ensemble accuracy. As future work, we're working in large deployments using data from different data sets and deep learning models and adaptive ensemble strategies to compare with the solution, have more data about the to compare if this proposal is working. So that's it. Thank you very much for your attention. We'd like to.
So questions?
Yes.
Okay, this is very interesting presentation. I want to ask you about the failure detections. So, described by the nodes. I want to ask you: is this vehicle also capable to detect the degradation of the nodes? Maybe not only 0 and 1 healthy and failure, but also we have early degradations, medium degradation, and simple degradation. Maybe like 4 stages.
In this case, VCube is one work as a failure detector. Traditional failure detector. So not just monitoring each node. So like a ping, like are you okay? Are you alive? And then it's just to remove or consider the ways of the answer that are from the node. But it's just failure or not failure. Okay. There's no correct wrongs. We actually are working on a new model where we use some impact factors. So a node has an impact factor, and you can summarize the impact factors of many nodes to get a threshold, for example, and then you can have different levels of trust.
Okay, so
It's a different model. In this case, it's just a traditional figure detector model.
but it's capable to experiment.
Yeah.
Okay. Thank you.
Oh, okay, thank you again. So the last presenter of this session is Nilsson Lazarin. With the work whose title is An Operating System Infrastructure for Embedded BDI-based Multi-Agent Systems.
Thank you. Hi everyone. So it's it's part of my research in my PhD course. I'm a student in University Federal Fluminense in the Computational Science program, and my professor in CFET. So the artificial intelligence of things is a new approach that joined the artificial intelligence and Internet of Things. And with this approach, it's possible to embed the agents directly in devices, in the IoT devices that can perceive and act in the real world environments. So some works have produced a multi-agent system, only multi-agent system embedded in devices in real world applications that present some advantages, like a parallel and asynchronous nature of the multi-agent system, and it's possible the distributed decision making applied by the agents. BDI agents is a kind of agents that is produced using a mental abstraction. As a BDI is belief, design, intention model. This model represents in a software how the human mind works. This agent extends the idea of the autonomous agents. Autonomous agents has autonomy, reactivity, proactivity, and sociability. And when you put the cognitive layer in these agents, the agents can exhibit a action that try to achieve some goals, some specific goals to applications in real world. So BDI agents enable this connective layer in embedded systems, so we can produce cognitive hardware. But the strong abstraction provided by the BDI approach introduced some challenges. That is the performance and the resource consumption and the hardware, and the dependence of the integration of infrastructures and the frameworks to provide the run agents in a robot, for example. So the problem definition is that the computational cost of the BDI reasoning cycle and the complexity to develop the process highlight the development of BDI agents and embedded platforms. So we propose two researching questions. That is, can the use of the dedication operational system reduce the complexity of the developing in BDI agents? And the second, is it possible to improve the performance of BGI agents in research constrained platform? To understand how BGI embedded systems currently being developed, we propose a review mapping using a snowballing approach. We start with the seed used in this snowballing was the RAW in 1996 paper that proposed the BGI agent language, the agent speaking language. So we put this paper in the Scopus base, look for the citations, filtered by years, filtered by title, filtered by area, because we want to found papers about embedded system with proof of concept and the real world application. And finally, of this process, we found 16 papers about this kind of system. The state of art in this paper, we can emerge layers of developing system. Multi-agent system is composed using BGI is composed by 4 different layers. That is the action layers, where the sensors and actuators act in the real world. The controlling layer, where we use a low-end IoT device like Arduino or other microcontrollers. An interfacing layer that needs exchange the message by the sensors to the agent's mind, and the last in the reasoning layer, where the agents are hosted to deliberate, receiving the perceptions from the environment, deliberate, and send commands to act in the real world. The development process of BGI multi-agent system bed has 5 different steps. First, we need to provide a device that design the system physical, and the second steps, we need to implement the firmware that get the sensory from the real world and translate in information to the agents. The interfacing layer is connecting a lot of microcontrollers that act in the real world to mind of the agent. And interface programming. The agent programming is the program of the agent that will run in an embedded system, and the service manager, when the design needs to configure the operation system, service dependencies, and a lot of things to allow the running of the agent. In this mapping, we could found 9 requirements to develop an operational system specific to BGI agents. That requirements are remote multi-agent management to develop access the agents running the system, and the start and the stop multi-agent system remotely. Connectivities that enable the agent, the connection of the device in the network to allow the agents live and join the multi-agent system, a network zone, a Wi-Fi direct, remote firmware management, BGI compliance, because it's a specific kind of system, and a lot of requirements. So, and finally, we can observe that a lot of solutions that exist in the literature that was used along the years, none of them fulfill all of the requirements to run a multi-agent system. So the absence of operational system level to this specific agent to support the development, support the management, and support the operation system is absent. So we propose, we formalize a 5-layer architecture to produce a BGI multi-agent system embedded that use the acting layer, where a lot of sensors can be used connected in the GPIO in the microcontroller. The microcontroller running the firmware. The microcontroller is connected in a high-end IoT device like a Raspberry Pi board. BGI agent framework where this agent is living, and operation system layer, a management layer with a lot of services to allows the systems. To evaluation, we propose 2 different scenarios. We use an embedded system. We host in a Raspberry Pi Zero W, 1 gigahertz single core, a healthy gigabyte memory, and the first evaluation was in design time. We want to know how many times, how time is needed to prepare the operation system, develop the microcontroller and firmware, and deploy the BGI based agent reasoning to run in a prototype. For example, we're using this tractor running only one agent in this case. This prototype run with a microcontroller inside, controlling the sensors and the actuators, and the Raspberry Pi Zero run the multi-agent system. So we compare with a general proposed operational system. We use the Raspberry Pi operational system, and we compare with our specific proposal. We name it the Sean OS multi-agent system. To prepare and provide the configuration of the firmware and the agents, use a general proposal system, we use 70 minutes, and using the specific system, you spend only 16 minutes in this process. We represents a reduction in the 77% of time to set up the system, a complete system. It's a good news to the developer of a embedded multi-agent system. The second evaluation, we analyze in a runtime evaluation. We use a multi-agent system with 2 agents, in this case running in the Raspberry Pi Zero, and using one Arduino. In this example, Arduino is running as a random number generator, and one agent gets a random number generator provided by the Arduino, and send it to other agents to compute a Diffie-Hellman cryptographic public key. And when the second agent computes, the agent send for the first the result, and this agent get the next random number generator to produce another key. And we compute how many keys was produced in a minute. You name it is a perceptions per minute in this process. Okay, and when using Raspberry Pi, compare with our proposed operational system, you can not see reduce from the consumption of memory is almost 15% lower memory, and the use of swap memory, the disk memory, because the disk system has a little quantity of memory, and the use of swap was reduced to in 46% of the consumption of swap. And the consumption of the CPU is the same, is not a big difference, and the consumption is a little bit more efficient in the consumption, but is not important. And when comparing the perceptions per minute produced when using the proposed operational system, we can perceive 7.2 more perceptions per minute. So the agents can perceive the environment more times in the same slot time. Okay, so it is this multi-agent, this operational system for multi-agencies, cognitive agents, is available in SourceForge. We provide versions for all family of Raspberry Pi, from Raspberry Pi 1 until Raspberry 5. In the 3 different versions, ARM version 6, ARM Health, and ARM 6.0 versions. So we produce a BGI based operational system focused in this case, and the future works we includes extended this operation system to support others different frameworks, agents, and then BGI or others approaches in agents. So a page with the results of the review and the source codes is available in the internet. Thank you very much.
Questions? Okay.
Just out of curiosity, you're doing your PhD on CoreOS.
Sorry?
Your PhD,
PG students.
it's on CoreOS. It's going to use PI agents
In our research, yes, we are working with embedded agents.
In your deployment, you just poke the Arduino on the desk for random numbers and.
Yes. In this case, where we want to compute how efficient is the proposal, so we deploy a firmware with a random number generator. One agent is accountable to get this perception. So the agent get perception and sent to another agent that is accountable to compute a different cryptography key. And when the second agent done, they send the reply to the first agent, and the agent get the second, and the send in this process is stopped in 1 minute to compute.
Eventually, do you think about doing something with Arduino, like actuators or sensors, manipulating hardware? That's much more interesting. Arduino is a very fun tool.
Yes, we can use Arduino PIC or others other microcontrollers. The level of microcontrollers can be used at anything microcontroller that is connected in the serial interface of a Raspberry Pi, because the agent is hosted in the Raspberry Pi. The agents run in the layer of reasoning, and the agents can leave and join this this device embedded from network, so an agent can go out from a system to acting in the other system, but the hardware is state, and the agent can join and act perceiving, get the perception of the environment and the action when is act.
Thank you very much.
Questions? Okay, thank you. So, thank you all. I'm closing this session. So, thank you, everyone. Now we have coffee break. Okay.
Acho que pegar mais água ali.
Igual.
Estão todas fechadas.
Não, assim. Tá muito calor. Vou pegar uma aqui.
Fora.
Tem aí só para ainda aí.
Água?
É.
Tem. Agradável aqui. Pegar uma?
Eu deixei minha mala no hotel para dar uma voltinha no centro.
I think it's really